Good afternoon, everyone. Thank you for joining another session of the GSE UK conference. Today we've got Barton Robinson. He's the CTO and founder of Velocity Software, and he will be talking about capture ratios for SMF. Any questions that you may have, please raise them in the chat box, and Barton will be answering them throughout the presentation. So with no further delays, Barton, the floor is yours.
Yep, and since I can't see the chat box, if you could please let me know the questions as they come in.
So we will.
All right, so this is a ongoing research project for myself that I've been working on for quite a while. And I started looking at the SMF about 3-4 years ago. So talk a little bit about who I am and why do I care. And for me, it's we used to have a term on Linux, it was BOGO MIPS. And if you look at it, bogus data in, it's bogus data out. And that's really what I'm looking at, is just the quality of data and making sure the data is accurate. I'll talk about where the data is from. I'm going to talk about several different platforms. I've looked at Prism an awful lot, and I think people really need to pay attention to that. I'm going to look at VM first, just because that's where I spent a lot of my life. I'll talk about what I've learned in BSC and Linux a little bit, and I'll talk about zOS, Kix, and DB2. And hopefully we all will learn Wales together next year. So for those of you that don't know, I was in Washington System Center for 3 years, a long time ago, with VM performance responsibilities. Back then, it was somebody had a problem anywhere in North America, and I got to get on a plane and go talk to them about it. There was an HPO tuning guide that I was the author of. I was the VM HPO tuning guide. I left IBM as a senior manager in the IBM Systems Evaluation Lab. I am the founder, CTO of Velocity Software for the last 33 years. So, and we do performance management development, and I really focus on the VM side, but we've added Linux as it came up, which included then WebSphere and Oracle as the applications. Added network data, look at VSE now too, and of course now there's zOS, Kix, and DB2. So, when I look at performance management, I'm really talking about to me, there's pillars. Is capacity planning. Everybody has capacity planning in our environment, in the Z environment. It's large, it's capital expenditures. You need to make sure you are doing it right. Some of the numbers are pretty large. Performance analysis, you need correct data for. Performance analysis is solving performance problems, current performance problems. Finding out what the problem is quickly. Chargeback is something that's critical in most mainframe environments. Just having data for the chargeback so that you can charge the right applications, the right departments for their utilization. And then setting operational alerts based on whatever performance metrics you have available. Business decisions are hopefully made based on real data. You look at making decisions based on bad data and get bad decisions. So we're looking at better decisions based on correct data. That's really my focus on this whole presentation, is that how correct is the data, what's missing, how much is missing, and how do we validate the data. Some of the things that I do is just I challenge some of the old traditional wisdom. And when I look at, especially when it comes to zOS, when I look at some of the topics out there, when I look at capture ratio out there, there's some traditional, and I look at it from my perspective. It's that, well, wait a minute, there's something missing. So, and if there's something missing, well, how much is it, and really what is causing that? When I looked at Linux, the first time it was virtualized, a lot of installations were using the Linux reported CPU metrics, and I did a demonstration for one installation. It's wrong by 2 orders of magnitude. Right? It was actually wrong by a factor of 89, but they were looking at their performance monitor. and I was looking at the real life data. And back then, there's a lot of conclusions that, well, mainframe was really slow and was really bad. It's because they were looking at the wrong data. So if you correct that data by 2 orders of magnitude, it makes a rather large difference on how the mainframe was viewed. And I'm not going to talk about SMT today. Things don't really add up there very well. There's a different presentation on that. So when I look at capture ratio, what I want to know is, where does all of it go? I don't want to know where the workload is. I want to know where 100% of the resources is going. If I know where 100% of the resources is going, that means I know where all of it is going. If I'm missing part of it, then that says that, well, maybe my other numbers are incorrect. If I say that, well, my capture ratio is 80%, well, I don't know, but the other 20%, I don't know if my 80% is correct or not. So I always look at the 100% as the target. I want to know where all of the resources are going. And I will start with just LPAR, just from that perspective. But if you look at the LPAR platform, there is a physical overhead, and pretty much every platform has this as well. There's a physical, just sort of an operating system platform overhead. There's a workload management overhead, so it's a logical overhead in LPAR terms. And then there's the actual workload that is using the cycles for real work. At some point, there's idle time, and then there's what's left is uncaptured. And it's that uncaptured that I'm really targeting. Okay, what is that uncaptured? Why is it uncaptured? What is actually going on there? When I look at the different platforms, how close are they to 100%? And when you look at our highest level platform, Prism LPAR, yes, the capture ratio is very close to 100%. I'll show some metrics that say it's not quite. When you look at VM, yeah, it's been 100% since about 1989. Linux, when Linux came on around 2000, yeah, we have pretty much 100% capture ratio there, and VSC as well. zOS, not so much. And the problem I have with zOS is the platform really does not report what the platform uses, whereas all of the other platforms report what the platform uses. So the question is, well, what is the actual overhead of the platform? And when I added up all my job data, did it actually reach the right value? And it's very hard to determine that in zOS, to make a mistake or not. So I look at capture ratios as validating the data and the instrumentation. If I know where 100% went, I know where 100% went. If there's something missing, then I don't know if my metrics are correct or not. So part of this is just validating instrumentation, is it complete or not. When you look at the Prism LPAR data, we look at assign time. Assign time is what is given to the operating system, given to the LPAR. And I'll look at it from both the SMF perspective and the VM monitor perspectives. And a lot of cases, I try and show the fields that I use. If anybody wants to try and do this with MXG or whatever they choose. So when I look at SMF 70, I look at, well, what fields are there that show the system overhead? And it's pretty hard to scrape out. When you look at from the VM side, it shows exactly what the system overhead is, and things just add up to 100% when you get it right. So when I talk about every platform provides exactly the same thing, we always get the physical overhead, which is the platform overhead. We always get something associated with the work. There's the time doing the work, and then there's the overhead of doing that work, which is maybe time for doing IO, time for taking interrupts. So, and then there's non-captured time. And sometimes non-captured time is just interface between the platform. So when you go from LPAR to zOS or LPAR to VM, there's something missing. So even though we say we assigned this amount, the operating system does not see that amount. So I'll look up at that. And it's, you know, when I look at it, it's 1%, about 1%. Sometimes it's higher than that. So most of my analysis I do just on a 1 minute granularity. I know the zOS world, they think that the overhead's too high, or I don't know, they don't do it. VM, we pretty much do it all the time on a 1 minute. Linux, we do it on a 1 minute granularity. VSC, we do it on a 1 minute granularity. When I look at the interval, so we have an interval, and we try and align everything to that interval. And you look at the components within that interval of what we're trying to measure. We have the system overhead, and then there's whatever's going on, whether it's the process, the job, the region, the virtual machine, whatever platform you're on. There's all these different components that we then need to add up to say, okay, this is what happened during that interval. So when we talk about the capture ratio, really we're looking at accumulating all of the processes, all the work processes that happened during that interval, add it up the system overhead and see if that adds up to 100%. One thing I point out is when I look at both zOS and look at the way we collect some of the data, the intervals aren't exactly aligned up. For us, for Linux and some of the zOS stuff we're doing, the interval might be a few seconds before our VM interval. So then when we're trying to compare, sometimes it's off by a couple percent. So, and I'm going to focus a little bit more on that. You know, there's a lot of work to do for me on the other application platforms later. So I look at the workload capture. There's really 4 different kinds of workload that we capture. There's the work that starts prior to the interval. So we need the point in time where it crosses the interval. We need to know what that CPU count is. And then there's work that keeps going. So if you look at the system tasks, the long-running jobs. So to collect everything in the interval, we need timers that we get at the end of the interval and at the beginning of the interval. Some of the work ends at during the interval. For that work, we need a transaction kind of record. And from that transaction record, then we need to know where it entered the interval. And so then we have the result at the end of the transaction. So there has to be a decent transaction model. That's a job record. In VM, we have virtual machine termination records. In Linux, we don't have that transaction record, so there's something different we have to do. For transactions that actually start during the interval and end during the interval, then we really definitely need the transaction model. That's a transaction. For work that starts during the interval, we always can assume that if the metric start at 0, and we just need to have the cutoff of the interval end. So at that point, those are the 4, and every single platform has some version of those 4 types of work. So if there's multiple CPU data sources, it's really nice if they agree. If they don't agree, I go back to Linux because the data was totally bogus when it first hit the virtualized environment. And way back when, DAWs, VS had the same issues as well. So the question is, if they don't agree, then who's right and who's wrong, and how do you correct that? So for VM, I look at LPAR data, and we have basically the same data as what shows up in zOS. We have the LPAR virtual machine data, and we have the LPAR physical overhead. This is the platform physical overhead. The SMF 70 groups that together. So from a VM side, once you get inside the platform, we have this CPU data, CPU by CPU. That's at the system level. And then we have virtual machine records that show the activity of the virtual machines. There's also one more data source. We have the hardware statistics. So we can look at which is considered the same as the SMF 113, the MFC data. And this is supposedly what it does. It measures the cycles consumed by the hardware on behalf of the operating system. So you would expect that what the hardware measures was the same as what the LPAR provides, or that the operating system claims that it uses. From a Linux perspective, we do get the kernel information, we get the IRQ information, we get the process information. But from a higher level, if Linux is running under VM, we also get the virtual machine data. And we're pretty comfortable with the virtual machine data is accurate to the microsecond. So we know that that's accurate. So then it's comparing what we get from the kernel and process data from Linux, making sure they match. Early on, they didn't match at all. So we had a prorate mechanism to take the data we get from Linux and prorate it to 100% of what we knew was actually true. So VSC, we get the same virtual machine data that's running under VSC. And from VSC, we also get the system data and the partition data and job data. So we have multiple metrics for each platform to compare. When you get to zOS, we get the highest level is going to be the Prism LPAR information. And unlike the other platforms, zOS really doesn't report what it uses in terms of system information. It's really expected that you go get the data from the LPAR. So we have only really one metric. We get the LPAR time for zOS, and we get the hardware SMF, which is again interesting. So you would expect that the LPAR logical time as provided to the LPAR was identical to what the SMF 113 reports was actually used. And there is a gap in between those. So, and I really think that even if it's 1 or 3%, but when you're really trying to do accurate chargeback, probably need to pay attention to that. So when we look at comparisons, we'll compare the logical, we'll compare the job data, compare the hardware SMF 113, and then we can go into the application subsystems, which I found interesting, just looking at kicks, how good's the capture ratio for kicks, and also as well as DB2. So one thing I'll point out, all my metrics are in terms of one CPU. If they use 60 CPU seconds, that is one CPU. If they use 120 CPU seconds within 1 minute, that's 2 CPUs. So it just makes comparisons simple with no percents of a percent. It also means that if engines are parked, for example, of course, they're not using CPU at that point, and then they're off the chart. So we don't need to worry about them. So when I look at application subsystems, it's the same work. There's many transactions. They all have that same 4 categories. There's going to be long-running transactions. There's going to be transactions across the interval boundaries. And again, the objective is to capture all transaction data, add them up, and make sure they align to the reality provided by a higher level, in this case, the SMF 30 records. But we can also then group by transaction ID and do grouping, and those groups should add up as well. So when I look at the transactions, really I'm looking at how do you group for capacity planning, how do you group for chargeback, how accurate is the data that we're, and is there something missing? And this is always a iterative process. So when I look at every platform has these 5 components. There's always the physical, the logical. Some platforms provide idle time. Some provide the system time. And then what I'm looking for is the uncaptured. So I'm not going to talk about steal time. Steal time is a concept that came up. And it's actually how they fixed the Linux bogus numbers. In a virtual environment, sometimes the underlying CPU is just stolen, it's not there. So that takes away time. So when you look at adding up the numbers, it's really, you look up the physical time, the logical time, the work time, the idle time, plus the steal time. That gets you to your 100%. So, but from my perspective, it's not really relevant for my capture analysis. I'm just looking for CPU cycles that are being used. I'm not looking at reasons why they're not being used. And the same thing with parking. If an engine is parked, it's just not relevant for capture analysis because it's not using cycles. That's more relevant from a performance perspective. Okay, so the objective is to know who's using a CPU and why. And I just look at it as, okay, on a current engine, we got 5.2 billion cycles a second. Who's using them? And when I look at the 113 or the MFC data, I can figure it out. So, and it really comes down to if uncaptured CPU is 0, then you know what's happened. And it also means that the platform is fully instrumented. And you can use the data for business decisions. When I look at data on any platform where it's not complete, then then you have to know, well, okay, do I go look at this, or where's my crystal ball? So this is the chart I'm going to build, and what I'm going to do is just show what is the management overhead. And I get asked this question a lot. Well, what is the overhead of running under VM? What is the overhead of LPAR? What is the overhead of zOS? And then the logical, so the zOS number is the one that's not reported. And then what is the logical overhead? And then I look at what is the uncaptured. So from a VM perspective, when you look at it, I'm looking at virtual machines. Actually, I'm sorry, this is from the LPAR perspective. From the LPAR perspective, looking at the LPARs, and of course LPARs don't really come and go, right? They're pretty much static. So, but we get the interval start, we get the interval end information. zOS and VM do it very differently, but we get the identical information, and we get the physical overhead of the LPAR. So we always have the same hierarchy of data. We get the transactions, we get the overheads, and we get the platform overhead. And I like to start with LPAR just because it is the simplest. We all have LPARs, and just since it doesn't really have a transaction model. So this is the kind of data we get from LPARs, from the LPAR data, and we all get exactly the same data. In this case, I group it by LPAR by processor type. So in this case, this LPAR has 2 virtual CPUs in it, and their accumulated CPU is 84%, 84.2%. And in that LPAR, just know that we're running VSC and we're running zOS on the general purpose engines. And then we have our IFLs, which we're running VM and our Linux workloads. So when I look at where the data comes from, right, we get it CPU by CPU, and then we can look at LPAR by LPAR. And then if we add up all of those LPARs, then it's going to add up to what was actually consumed. So, and I'll be looking at data. These are two of our zOS LPARs. They each have 2 virtual CPUs. Each of them are using 56%, and a lot of our workloads we replicate for performance testing reasons. Then at the end, to summarize everything, and this is what the summary would look like. So we have, in this case, we only have 2 general purpose engines, of which 200% is assigned. So we're pretty comfortable that the HMC, the Prism, is telling us 100% of where the data is, where the CPU is going. In this case, the physical overhead is 0.1% of one CPU. The logical overhead is 0.1%, and then the rest of it is allocated to the LPARs that have general purpose processors defined. We have 4 IFLs, and we have the zip, so that we can do some zip testing as well. But I put the fields here for LPAR time. For the physical time, it comes from this one monitor record, SYT-CUM. The logical engine data always comes from the SYT-CUP. And these are the same data that comes from the SMF 70 records, just in a different format. So when I look at LPAR, when I start to build my model, how much do we lose? We don't lose very much at the LPAR layer. And so 99% of it's going to be work. Uncaptured, I can't detect any uncaptured at this level. However, when I looked at the hardware level, then I start to see something a little bit different. So I'm going to look at VM first, just real quick. And this is the kind of data we get from VM. We get the emulation time. This is time assigned to virtual machines. And now this is at the system level. So engine by engine, we get this. In this case, 45.9% of the time it was assigned to real work. 0.6% of the time it was user overhead. And we get this magic number is 0.4% system overhead. So this would be comparable to that physical overhead at the LPAR layer. So we added up and we have this number. So this 377.7, that is the total emulation time and the total user overhead. So we have metrics for that, and that comes from the system level. And we don't get those metrics from SMF, at least as far as I can tell. And then there's a steel metric. So if we do get idle time, and each engine reports idle time. If we add all those up, if you add idle time up to total utilization, subtract it from 100, and that's going to be your steel time. Because we thought we had the engine, but we didn't, because it was stolen from underneath us. Okay. So first level analysis, we have the LPAR prism. Then we have the secondary. We have what's going on in VM. Then we have which is at the processor level. And if we want to compare those, so I did a comparison just to look at what came out of the LPAR. And so this is data provided by the LPAR HMC, and this is data provided by VM. So you would expect these numbers to be equal. That's why when in zOS they expect you to use this number for this purpose. It doesn't really work. So what VM sees is 61.2% of an engine, whereas LPAR says I delivered 62.4% of an engine. So we lose something, right? And at the end of the day, you add up the numbers, and there's quite a difference in what was actually delivered or what actually was consumed. So emulation time is the time where the virtual processor should be executing. Right? So it's 61.6 versus 61.2. So it's a little bit less. Okay. So I just put the CAPS ratio here, and the CAPS ratio it comes out to be about 99.3, which means we lose about 1% on this system. I've seen systems higher than that, seen systems that are comparable. So that just says that you need a 1% basically fudge factor, just for prism overhead. And then there's this capture ratio. We're missing a percent there. And then we have the system overhead, which is another overhead. So when you're building up the model, we're losing CPU as we go. And it's just important to know where we're losing it. So just the relationship between the LPAR delivered and the LPAR received was interesting to me. So, okay. And then yeah, SMTs changes a lot. So I changed my model because the capture ratio is really 99%, because there is some data missing when we look at what LPAR says it delivers to what is actually received. Okay, so we looked at what VM delivers per CPU. We have all the information delivered per CPU. We also get information for the workload. In this case, we get information for each virtual machine CPU. And I put up the record names. And we also, from a transaction level, we get a record when a virtual machine logs off. So we looked at this. So the totals of all the virtual CPUs add up to 377 emulation time. There's user overhead. And then when we add up the virtual machines, so here, in this case, it looks like it's a WebSphere DB2 environment, Linux servers. So here's our 377. So the system reports 377.7% at a CPU by CPU granularity. We add up all the virtual machines and we get the same exact number. So our capture ratio from a virtual machine perspective is 100%. And you do the delta between those and you get your 5.4% of user overhead. So when we look at just what's happening on VM, yeah, there's some system overhead. In this case, it was about 3%. There's some user overhead, it's about 5% of the workload. But the fact that we have two different data sources and they agree to 4 significant figures is very good. So when I look at just my model, it's 1% of overhead for management, 2% for logical, and there's work. Uncaptured, it was 0. So for time constraints, I'm not going to go into the VSE, but just want to go through a little bit of, we look at jobs the same way we look on zOS. In fact, we have some ratios here we look at, and it's the overhead. So for virtual machine perspective, we have some overhead we look at. So VSE is going to lose some of their. So I have, I think, 65 slides, and this is a general purpose presentation to cover all the platform as people are interested. For VSE, yeah, we have the partitions and job records, which would be comparable to zOS. And you can see the capture ratios. So from a perspective of, well, what do other platforms provide? And VSE does provide some system metrics, as well as the partition metrics, and we have a good capture ratio, so we can deal with that. So I'm going to talk a little bit about Linux, just because it's interesting to me, and I think most installations now are starting to look at in the Linux direction if they haven't there already. Linux also provides all of the system metrics in terms of IRQ, soft IRQ, kernel metrics. And so when we add up the process data to the system data, that should add up to 100%. We capture all the Linux data via SMF. So there is a time delay as we capture the data. And that's just useful to know. And sometimes the numbers are off by 1%. Well, it's a synchronous process in getting that data. Sometimes it's a little bit more synchronous than others. So the critical thing in Linux is understanding where the CPU goes. When a process comes and goes, there is no process record, there's no transaction record, but the CPU does get allocated to its parent process. So you really need to build a parent-child tree. And I'm going to talk a little bit about that. Just from a VM perspective. So from a VM perspective, these are several intervals of one Linux server. And this is the virtual time allocated to that server. And then when we look at what Linux says it used at a processor, so Linux provides the CPU by CPU information as well. And we sort of can look at the data between the two. But remembering that if you look at the intervals, they're never exactly the same, and that's just because the time of collection. But overall, it was pretty close to 100% capture ratio over time. So, so from the Linux data, we get the management overhead. We can get from the process data, we can get the logical overhead as well. So when I talk about the critical part in Linux is there's processes, there's a process tree. And I've seen different agents not show up at all. So somebody will say, well, my agent doesn't use any CPU. Well, it's a short-term agent. So if I build a cron job that puts off short-term agents, you will never see those agents because you never look at them when they are actually running. So what I show is, yes, there is a process tree. And if you look at my DB2 high level, it doesn't use any CPU either. But if I looked at cron, so this is the CPU, this is system time used by cron, and basically the overhead, logical overhead of cron, and the user time of cron. It's always 0. Why? Because it's spawning tasks that are using it. So if you're not checking the children buckets of CPU, then you can say, well, my process uses 0 CPU. And I've seen people make that mistake. The only way you can get a high capture ratio is to inspect the CPU buckets. And if you look at something like, if some of these DB2 or Oracle processes go away, where does their CPU go? It goes to the children buckets. You have to just be aware of that. But we do get a high capture ratio, and you can see that in this case there's several servers, and the capture ratio is at 100. And you say, well, how come it's over 100? Just because there's variation in the way we collect the data. So this one time. So that's adding up the system data, the process data, and we get 100%. So, and you think about some of the Linux servers, they might have 1,000 processes. So you collect that data synchronously, and you expect some small variation. So we're looking at that, and we've looked at the DB2, we looked at Oracle, we looked at WebSphere. You can get the 100% capture ratio there from the system level perspective, from the application level perspective. Okay, so Linux is all good, and if you look down, pretty much every platform it's sort of in the 1% range. Linux may be a little bit high. Logical Linux is comparable, maybe to VSE. The real work is comparable. So then we get to zOS at the point of the presentation, and the object is to show system overhead. Well, that's not reported, so we have to figure it out. Hopefully we get it right, but since the system doesn't present it, then it's a mystery. So uncaptured. So really with this uncaptured, for me, the objective is 0. And I was surprised to find out that it's not the typical objective for the platform. So if the uncaptured is 0, the platform to me is fully instrumented. If there's crystal balls involved, then we have a problem with the instrumentation at some point. So we looked at the Prism layer, and then we want to look at, well, what does zOS actually see? We know what the LPAR provides to zOS, but we don't know what zOS actually uses. So we do have the SMF 113. I thought was pretty interesting. And then we can look at the SMF 30s and then see, well, what are we missing? So when I look at the data, there's always, at every layer, there's something missing, right? So if you look at, from the LPAR perspective, well, the LPAR layer goes over to zOS. Off zOS, we lose some overhead. There's going to be some logical overhead, and it's uncaptured. It turns out probably this red bar should be in black. And then we get to DB2 or kicks, and we're going to have the same layer. So every time you get lower and lower and lower. And the question is, well, how much is that red bar? How much is that yellow bar? And more important to me, how much is that black bar? Right. So looking at the 70, there's a weight field, and traditionally, if you have dedicated processors, that adds some value. I can't see any value in that anymore. So you really have to look at the LPAR data, and there's basically the PDT, which is the assigned, and the EDT, which is the real work. Same as we get in DM. So the delta between these two is the logical overhead. You can't really compare the zOS data to the Prism data. So because we're using the Prism data for the zOS CPU data. So I will do a comparison with the 113. And I was actually surprised. So the 113 shows cycles consumed by the CPU. And you would hopefully that they're very close. In VM we saw about 1%, zOS we see a little bit more. So this data is what is provided by the LPAR as the virtual time. This data is provided, that's what we get from the MFC data, the 113 record. And there's quite a difference between what was given to the LPAR and what was perceived to be delivered by the zOS. So this number here, this percent here, it's just we know the cycles on the box, 5200 for 5.2 gigahertz. We know how many cycles was actually used as reported by the hardware. There's also the instructions, and then I look at the ratio of cycles to instructions quite a bit, and that's used in a different category. But for my capture ratio, I was looking at, well, here we have a CPU utilization metric. We'll use it to see how close it is. So we're losing something there. Looking at the 30s, we can add up all the 30s and we get to a 8% utilization. So I'm pretty comfortable with that. The 24.88 is the total of all of my SMF 30 data, all of my active regions jobs during this interval. And I can look at the SRB time, right? TCB time. So, and you can tell that in this case, our workload is going to be the KICS workload. So the question is, do they match? And just if you want to look at my calculations, for the 30s, these are the fields that I add up to be my total job data with the different SNF types. Okay, so when I build the model, I look at what I get from the 30 data, I compare it to the 70 data, and then I look at the ratios of the real work, the relationship of the logical overhead, and then I try and find, well, what is the supervisor? What is the overhead time? Okay. So this is what I came up with from the SMF 70, and this is, I'm not using the 113, I'm using the SMF 70, what you're supposed to be using, so which explains for part of my capture ratio delta. If I add up the two general purpose engines, it's 26.9% of an engine. If I add up my 30s, I get 24.88. So I'm pretty happy with that capture ratio. What am I missing? I'm missing a few percent, but I guess that's what 8% I'm missing. So, and I can look at my logical overhead because I look at my SRB time. That would be considered logical overhead. So I can start to build my chart that way. And looking at it, two of our LPARs over time, just to see, well, is it consistent? Capture ratio. So these are our two of our zOS systems. 92.7, 92.6, 92, 92. Okay. And so it is pretty consistent, but LPAR to LPAR is different. So I think it's relevant to look at, well, why is here my capture ratio? Well, I'm losing 15% on this LPAR, I'm losing only 8% on this LPAR. So is that system time, or am I losing something else? And I think that's a critical question. Maybe I'll have an answer at some future time. So I look at the capture ratio, okay, management time, that's the system overhead, that's a mystery. Right? I also look at my capture ratio, it's very low. So I'm definitely missing some CPU. Is this 8 to 15% my system overhead? And in which case, as compared to other platforms, that seems very, very high. When I look at the logical overhead, I look at as compared to other platforms, it's also very high. So there's a lot of numbers in there that I think when you're doing capacity planning, you want to be focusing on, well, how much work you're getting out. So next step was I just looked at KICS, just look at what I can do. And for KICS, we get the transactions, we get them on the fly. and we just process them on the fly. And for this example, we had almost 1,200 transactions, and we get for each transaction, and so I just grouped them by transaction ID, but I group them by transaction ID and by total. We get an average CPU by transaction, and that all comes from the 110, and that's pretty easy to do. So the question is, so we get the data from inside Kix. How does that match what we see from outside Kix? So from outside Kix, the Kix region says it's using 20.2%. From inside Kix, we add up all those transactions, those 1,200 transactions, and we get 19.5%. So I'm pretty comfortable that when I group my Kix transactions, that I have accurate information. If I can add up the 1,200 transactions and get the right amount of CPU, then my capture ratio is very decent, and I can show that the data is accurate. And you can see that LPAR to LPAR, that's in this case. And we have lots of Kix regions. I just chose these two systems. So, so you look at it, and the red bar for Kix is pretty low, as is the yellow bar for Kix, and the uncaptured is very low also. So yeah, just coming up with the numbers for the model, I looked at, well, I know from an LPAR level we lost 2, maybe 3%. From a zOS, we lost another 10%. From just the logical overhead, there's probably another 3%. So that gives us, looking at just Kix, what is available for real work? What should we charge for? Oh, yeah. Yes, exactly. It is variable, and this is the start of the model. So if you have some Kix data that has higher variation, I would be very happy to look at the SMF data, 110s, and actually understand what that discrepancy is and how much it changes. So, but so from our different regions, which have pretty static workloads, yeah, we have a pretty high capture ratio, and you look at the logical overhead, and let's see, I guess I moved the numbers. So the next one I looked at was DB2, and just this is kind of a later project, and DB2 is a lot more complicated than Kix from a lot of perspectives. There's a lot more moving parts. But I was interested in just looking at the statistics, by the region, how accurate are they? Looking at versus the SMF 30s, and then I was looking at the transaction records to see, well, do they add up? And so the CPU, you'd hope would add up, but when you look at just the general statistics, so bear with me because I'm learning about DB2, but there's 4 components of the DB2 the database application, and so we have the CPU, and on this point in time we don't have much of a workload. But if we look at the total percent in use from the SMF 30 record, and then we compare that to what those statistic records, the 100 records, are reporting, they seem identical. So possibly they are identical information, but in any case, I feel comfortable using the SMF 100 statistics records. I'm looking at how much my DB2 application is consuming. So most 2 of our zOS are dedicated, or not dedicated, but are not under VM. We have some under VM just so we can tell the difference. And then we have all the parm set so that we get the data. So according to my zOS thing. Uh, okay, so from the 101 records, when we add them up, so in this case, there was close to 2,500 transactions. And you add up the CPU from the transactions, and I just did by transaction name. They added up to 0.6% of a CPU. So obviously our load is very, very low. When I look at the SMF 100s or the 30s, yeah, it was higher than that. So in this case, it was 84%. And since I really don't understand the relationship of the transactions to the database components or regions, I'm missing something there. But from my perspective, I'm looking at, well, I'm not that far off. At least I'm in the ballpark. So I've got some data. So thanks, Rich. So so far, when I look at it from my perspective, I look at, well, I want 100% capture ratio. So yeah, I'm not there on DB2, so I know I've got some work, but that's just something I started a couple months ago just to look at. If I can get to 100% capture ratio on DB2, I'm pretty happy with my transaction model. And so I can recognize what application is using the CPU, what transactions are using the CPU, and I can start grouping the transactions in meaningful ways. The first step is to work on that capture ratio. And I'm trying to work on that capture ratio too, the zOS capture ratio, just to get a feel for what's missing. And I've seen Peter Enrico's presentation on it, and yeah, so if capture ratio is low, you go look at these things, and with that takes a big book of things to go look at. So when I look at the capture ratios, I'm looking at, well, can I validate the data for capacity planning? And if I can validate that data, I need to know consumption, CPU consumption by application. If I'm going to do capacity planning for an application that's going to double in size, then I know that my numbers are accurate. I know how much I'm going to need or how much to plan for. From a chargeback perspective, I get a lot of chargeback questions. Everyone wants accuracy. And when numbers are wrong, and if people start to recognize it, then say, well, wait a minute, what's going on? And if there's a lot missing, then how do you charge for that? So then you have to put in a fudge factor for your chargeback. From performance analysis, if you know that you have a high capture ratio, then when there is a performance problem, you can say, it's okay. If it's a CPU performance problem, you can say immediately, it's this process group, or this process ID, or this SMF 30, this region is causing the problem. So it's very easy, and you can identify those problems programmatically very easily if the data is accurate and dependable. So I'm happy to evaluate data for anybody, especially anyone who's sat through these 65 slides in this short amount of time. If there's any questions, you can go off mute and we can talk for a minute. I think I've got an extra 6 minutes. So it was a little quicker than I thought to go through those. So I'm hoping to get more information on zOS, and I know there's some other fields there. There's some other ways of looking at things that I'd be happy to take suggestions for. If you have some data that you would allow me to evaluate, I'd be very happy to. For me, I've got a tremendous library of VM data. My library of Kix data is low, and I'd like to see more data to evaluate. Same thing with DB2, and we'll be doing MQ pretty soon as well, just for fun. So, on that note, are there questions or? Hi, Scott. So,
thanks, Barton. I don't think there are any more questions in the chat box, guys. If you have any questions, raise them in the chat box.
I could barely hear that. Was it? So I saw something with the 72 records, and yes, I did. I started looking at the 72 records.
Yeah, so there's an entry there saying 72 goal records can provide a cross-check.
An additional cross-check, yes.
Yeah.
Yep, absolutely. And I did start to look at that. But, this presentation took a few more months than I expected it to take. It became a lot more interesting. So, and for the kicks, yes, I mean, we get the point in time, and I can't remember which of the this is a subtype to look at, but yeah, we do get the point in time from interval to interval. But that's exactly the same analysis we do for everything else. So we don't really need to prorate. We actually get the hard metrics. So we get the point in time.
Excellent. Any other questions, guys? Well, Barton, thank you very much for this excellent presentation. We appreciate that. Our next meeting will be at 2 p.m. UK time, and we will be covering IBM zOS on the Z15 hardware. So if there are no more questions, we can close this session. Thank you very much. Again, Barton, thank you for your time to present this to us. Thank you.
Thank you, everybody, for showing up.
Thank you.
Bye-bye.